Hello everyone, my name is Jaydip Kuber Sawant. I am PhD student in Ocean System Engineering in JU National University. Today I am going to present about my recently published paper, Human Mimetic Sensory Interface to Neuromorphic Device and their Training Mechanism. In this, I will explain about how researchers are developing the neuromorphic sensors which can mimic our human senses. So this is my content, in which first I will introduce about the HMSIN devices, then biological foundation of human sensory interface, then HMSIN devices, and in this I will explain about neuromorphic vision, audio, tactile, olfactory and gustatory systems and its training mechanism. Then I will continue with the hybrid and multimodal neuromorphic sensors. Then I will conclude about this PPT. So what is the HMSIN devices? Human senses like vision, hearing, touch, smell, taste are highly patient and adaptive. They convert stimuli into spike-based neural signals. These neural signals are transferred to our brain, and then our brain process it, and then we can learn from our environment. We can learn about our environment from this stimulus. Neuromorphic engineering aims to replicate these brain-like functions to the hardware. HMSIN devices combine sensing and synaptic learning in the one platform for intelligent perceptions. In this slide, I will explain about strength and weaknesses of these HMSIN devices. In the strength, real-time adaptive sensing, low power consumption, multimodal integration, and compact device architecture are the main strength of this device. In the weaknesses, it is cost effective, and in the case of multiple neuromorphic devices, we cannot fabricate the multiple neuromorphic devices. These are the biological foundation of human sensory systems. As we can see here, the eye converts light stimulus into the electrical pulses. Then ear convert sound vibrations into electric pulses, and touch converts our touch senses in electrical pulses, and nose and tongue convert the chemical stimulus into the electric pulses. These are transfers to the brain via the neural network. Then our brain converts them and learns about them. In this slide, I will explain about the neuromorphic vision sensor and its training mechanism. In this neuromorphic vision sensor, as our eye works, this sensor consists of multiple pixels, which detects the different light wavelengths. Like if you have IR light, UV light, or visible light, it will conduct differently as the light is conducting. In this case, when we apply the UV light or other lights, that time it shows different resistive state. So when by this different resistive state, we can train it like which resistive state is for which light. With this one, we can train this neuromorphic vision sensor. The next one is a neuromorphic audio sensor. In this case, we can use tang or ping as a sensor for the neuromorphic sensor. So when we use tang or ping, the vibrations of the sound, this detect by this tang and ping. When this tang and ping detects these sounds, it converts this vibration into electrical pulses, and these pulses are then transferred to the memristor. Then this memristor stores the data, store this wavelength, this pulses in the form of data. With this different frequency of sound, it can learn which sound is coming from the tang. Similarly, in case of neuromorphic tactile sensor, and in this case also we use tang and ping, which these tang and pings are convert our touch sense into the electric pulses. When this tang converts spikes pulses, these spikes goes to the memristor, and from these spike signals, it learns the which touch is what we are touching, what we are force, how much force is applied. Next one is the neuromorphic olfactory sensors. In this case, we have two different sensors, two different systems. First one is a gas sensor, which detect the different gases. Like if you apply SNO or WO3, then it detects. If you apply nitrogen or hydrogen, then it detects this gas and send the signals. Then the memristor stores the signals. When the gas sensor detects these gases, it changes resistance state. When if you apply hydrogen, then it will have some different resistance state, and when we apply the nitrogen, it will have different resistance state. So from this, memristor can learn which resistor state is for which gas sensor. The next one is neuromorphic gestalt sensor. It is similar with the olfactory sensor. In this gestalt sensor, we use different spices like sweet sense, sweet or spice, or other sense, like other chemicals. From these chemicals, it converts the chemical to the resistive state for the its sample, and different resistive state that different taste. The next one is hybrid multimodal neuromorphic sensors. In this case, researchers are trying to combine multiple sensors like gestalt sensor, touch sensor, vision sensor in one device. So why they are important? Hybrid sensors enable human-like artificial perception for next generation material AI systems. They are essential for applications such as robotics and smart prosthetics, autonomous vehicles, healthcare monitoring, advanced human-machine interfaces. How they are built and how they learn and work. In this case, we have two different senses, and like touch sense and tactile sense. These senses convert their electric pulses and send to the memristor, and memristor read these pulses and learn about these pulses. So when we apply single pulse, a single like vision sense, it will convert. The memristor will take this vision pulse, and when we apply the tactile pulse together, then the pulse will be like increased. So memristor learns like two signals are coming, and it learns from these signals. In the conclusion, HMSIN devices represent a new class bio-inspired systems that combine sensing, memory, and learning in one platform. They mimic human sensory organs like vision, hearing, touch, smell, taste by converting stimuli into the spike-based signals. Material-driven synaptic effects such as ion migration, charge trapping, and phase transitions enables efficient hardware plasticity. Neuromorphic sensory device demonstrates key brain-like functions, including learning and potentiation, memory retention, forgetting, and adaptation. Hybrid and multimodal HMSIN devices are emerging as the next step towards the intelligent artificial perception. Despite strong potential, challenges remains in the scalability, stability, and reproducibility. Overall, HMSIN platforms provide a promising pathway for future low power AI technologies. Thank you.